2020.
Recording has started. Okay, good. So this is being recorded. This is one of many training seminars that I have put together for Ben. It was one of the major reasons I was hired. So today's discussion is going to be centered around ASME pipe designations. We'll give everybody just a few minutes here, and then we can get started. I invited everybody on the list, so if somebody wants access to this, it'll be recorded. And they'll be able to listen in and follow along with the slide deck that was in the link. Normally, we do these trainings in two sessions. One session is kind of the presentation session, and the next session is there for questions. Matt Gildenhouse asked me to put this together for a larger group, so I made it a little longer, and we'll just have to answer questions at the end. I should be able to get through the whole thing. Mike, I started recording this. Everybody that was invited to this should have access to the recording, I think, or I can email it out to everybody else.
Yeah, we'll just put it somewhere on the server and link to it.
Okay, great. All right. It's 1 o'clock, so I'm going to go ahead and get started. This is being recorded, Hayden. Today's discussion was to be centered around ASME piping designations and testing requirements. This was something that Gildenhouse asked me to put together for the group. So what I wanted to go through today was some basic terminology. I then wanted to cover ASME B31.1. I wanted to cover ASME B31.3 and B31.3 for BPE. Which is higher purity piping systems, biopharma. I wanted to touch on the Section 8 BPVC, the boiler pressure vessel code. I've got a couple slides on ASME B31.5 and round it out with ASME B31.9. So let's jump right into the terminology. This will be the third slide. So obviously, as we just saw, ASME has various categories or classifications for different piping systems. ASME breaks these up based on the material that's being conveyed. What ASME does is they assign a fluid category depending on the hazard of the fluid and the type of fluid, whether it's a liquid or a gas or a viscous fluid. So we'll talk a little bit about that. We're going to, oh, hey, Dan.
Somebody, sorry.
Oh, that's fine. ASME also has different classifications based on the pressure and temperature of the fluid itself. So it's not just the material properties, it's the pressure and temperature of the fluid itself. And then there are some special requirements which we'll touch on with B31.3 BPE. So as industries go, industries tend to follow recommendations from ASME, API, ISPE, and other organizations, such as ASHRAE. So API is the American Petroleum Institute, and ISPE is the International Society of Pharmaceutical Engineers. So what you'll find is a lot of these different industries will kind of adhere to their own organizations, kind of like what we do with ASHRAE. But then ASME is also a code. So it's enforced by OSHA, it's enforced by state boiler inspectors and various other entities. And like ASHRAE, ASME is referenced in the ICC codes and the UCC codes. So this is building code stuff. But as you'll learn, a lot of these topics are really kind of outside the realm of your typical AHJ. So they rely on the state boiler inspectors, fire marshals, and they rely on the insurance providers in some cases to step in and ensure compliance with ASME. All right. So I wanted to jump into fluid categories a little bit. So there's a normal fluid, there's a category D, category M, and special fluids. So I wanted to touch on category D fluids and category M fluids. So a category D fluid is any fluid which is non-flammable, non-toxic, not damaging to human tissue. Very important to note, it does not exceed 150 psi, and we have normal design temperatures. So this covers almost all the fluids we deal with at NDBS. I'm going to switch this to actual presentation mode here. So then we get into category M fluids, and again, ASME starts with the fluid designation to determine which ASME code it needs to adhere to. So a category M fluid is a fluid service, as you can read there, where there could be a toxic fluid, a leak can cause serious harm, or anything that's above 150 psi. So I gave some examples here. We don't get into a lot of these fluids, but we do get into natural gas, which is explosive. I've worked around a lot of these chemicals. As some of you guys know, I worked in a chemical plant, so we had a lot of category M fluids running around. Just a fun fact, when you're designing in a seismic zone, if we're doing an industrial job or a pharmaceutical job or a manufacturing job, even though category M fluids may be in a small bore pipe, most of the time they are, if that pipe is considered malleable, it still has to be restrained as if it's a larger pipe size. So you can't take the exceptions when you're designing seismic and you have a category M fluid in a pipe. Okay, some more terminology. We're kind of going through some terminology.
Sure.
We'll jump into different sections. So this is a very common term used in industry, the MAWP. That's the maximum allowed operating pressure with one failure mode. So there may be an upset condition where a valve could get stuck open, or the process itself. It may be a chemical process that's exothermic, and the temperature may increase during that process, which also increases the pressure. So maximum allowed working pressure of a vessel or of a system is dependent upon the process itself. What you do not consider when determining your MAWP is a fire or an explosion that may occur around the pipe. That's not typically considered. It's again the fluid inside the pipe. So it's calculation, and when you're looking at your piping system, you have to look at your weakest link in the entire system. So an example might be if you have a piping system that's connected to a vessel, the vessel might be rated for 200 psi. You might have a class 150 piping system, but you might have a class 125 valve in that system, and you may have a flange that's only rated to 110 psi at a specific temperature. So you have to look at the entire system, and your maximum allowed working pressure of any system is always the weakest link in that entire system. Another term that you hear tossed around for MAWP is system design pressure. So when we talk about a class 300 or a class 150 piping system, we think of that as a system design pressure of 150 psi, maximum system design. In other words, what is that pipe or vessel designed to withstand? Of course, you may operate much less than your system design pressure. That is the maximum allowable pressure for that designed system. And when all these manufacturers list their working pressures, maximum pressures, they almost always normalize it to 75 degrees Fahrenheit in the United States. So if you're dealing with a hot water system that may operate at 180 degrees, that Apollo valve may not be rated for as high a pressure as you think it is. So you have to be a little careful when you start doing these kind of analyses. So this is a term, the lowest stress ratio, that's used when you're calculating your allowable working pressure, maximum allowable working pressures. And it is in the ASME B31.1 and B31.3 and in Section 8. So when you're calculating, like for a vessel, for example, when you're calculating your maximum allowable working pressure, you have to normalize the pressure based on your actual temperature and pressure that the vessel's going to operate. So it's a factor, if you will. ASME B31.3 actually calls it the R sub R factor, or ST over SD, which is the stress at the test temperature divided by the allowable design temperature stress. So if you start getting into these codes, you'll notice that the terminology is different between the different sections, but they really mean the same thing. It's not unlike building codes where, or ASHRAE standards and codes, where you may have a different committee or a different author that has developed this over the years. They like to use their terminology. The guys that are writing the other section like to use their terminology. So you always have to kind of get level set with the terminology, which is why I'm bringing all these things up. And I'll show you when and how these are used a little later in the presentation. I didn't put that little thing in there correctly. So minimum hydronic pressure test procedure. So here we're talking about hydrostatic testing piping systems. This is how ASME defines it. It is a documented procedure for testing of vessels or piping systems based on one of these two things. Pressure, temperature, which is around the worst case operating, or at a single upset condition, or a calculated condition, depending on which code section you're in. And I just popped up an example of an equation that's used as part of these calculations. All the data can be found in boiler pressure vessel code section and pressure piping section. So again, later on as I get into these sections, I'll show you what these what they're used for and how it applies to our everyday work here at NDBS. Single mode of failure is a pretty big deal. Most insurance companies will only require that an owner or a client consider one mode of failure. And so therefore, as design engineers or people out there in the field testing these systems, we're only required to design and test the system for that one mode of failure, and it's the worst case mode of failure. And almost every industry that you get into, they use MAWP as a terminology for piping or vessels. I wanted to just mention that, I'm not going to talk a lot about pneumatic testing. We do a lot of it here. MCAA, the Mechanical Contractors Association, has taken a position. They've written a position letter on pneumatic testing, and I've quoted it here. Hydrostatic testing is always a preferred method of testing because it generates considerably less stored energy. But they do list some exceptions there that will allow for pneumatic testing. If you go to OSHA's website, there are many, many documented cases of loss of life due to pneumatic testing. When gas is compressible, so when you charge up a system with air, it turns that entire system into a giant pipe bomb.
We had an incident in IFS not long ago. Just this year.
Now, hydrostatic testing is better because when the rupture occurs, because water is incompressible, that energy is released, localized at that site, and it's dissipated very quickly. So when I worked at the chemical plant, and most manufacturing plants that you work in, they do not allow pneumatic testing because of the safety concern. So I wanted to mention that, and for the purpose of the rest of this presentation, I'm not really going to talk about pneumatic testing. It's all going to be hydrostatic testing based. It's worth noting the exceptions. You may have some owners that will require pneumatic test, although I have yet to find one. MCAA is kind of putting that in there to let themselves off the hook. If you have a renovation project that's occurring and you can't find a way to introduce or get rid of the water or the testing medium, then it's allowed by the MCAA. And if you have a high purity or a system that just can't be filled with water, I'm thinking about a compressed air system. So typically in pharmaceutical, there's always a lot of overlap with the different ASME codes. If you have a high purity compressed air system and a low purity compressed air system, we hydrostatically test those systems in the pharmaceutical business. But you have to dry them out with nitrogen. So there's a purge time and a dry time associated with that testing. Clean systems, on the clean side of compressed air, you typically use DI water to test that. But if you have an ultra pure system, like a water for injection system, they don't want you to put regular water in that system because it will create impurities in the system. And so ASME has ways around that too that don't even involve pneumatic testing, special system testing. So I gave a link to the website if you guys want to research that further. I wanted to mention non-destructive examination. It's also known as non-destructive testing per ASME because you can actually, as I just mentioned, test an entire system by means of NDE on 100% of the welds and joints without hydrostatically or pneumatically testing that system. And there's examples of NDE that we get into. Power plants, pharmaceutical, and municipality systems use radiographic testing frequently. It's an X-ray. Ultrasonic is frequently used in industry. What we see a lot of is dye penetrant or eddy current testing. And there's a newer technology coming on the scene called magnetic particle inspection testing, which is kind of interesting.
Yeah, is that the one they called phased array?
Mm-hmm.
Yeah, use it a lot,
Yeah, it's really neat. So I wanted to mention that an authorized inspector is usually required to review the test, in some cases participate in the test. An AI is somebody who is usually certified as a Class 2 weld inspector. and they've gone through additional training and certifications. So we don't have many AIs around. It's kind of a specialty trade. A little bit more on terminology. The QA/QC program for a welded system may include any or all of these components. So I wanted to talk about each one briefly and just describe what it is, because you guys may run into this on a future job sometime in your career, where somebody's asking you for your weld maps. Where's your weld continuity log? So let's dive into this a little bit. So this is essentially a documented procedure for different sections of ASME code that require this. So these are code required documents that are included in the engineering turnover package, and they're also reviewed and approved by the owner while it's happening. So a weld continuity log is basically a set of documents that shows all the ISOs are in there, all the certs are in there, all the mapping and all the procedures are in there. So it's kind of the cover sheet, if you will, that describes this is how we're going to document all this welding that's going to happen. Welder certifications are just that. Each welder that's laying a weld has to go out and get the training. They get certified by their local hall or their local certification agency, and you have to get that documentation from them. A lot of times you have to get their social security number and their license number in some of these systems. Weld mapping is just a spreadsheet that correlates each individual weld with the fab isometric drawings. You might have fab welds and you might have field welds. And so both have to be tracked as to who made the weld and what was involved with making that weld, what weld procedure was used. In some cases you have to track what equipment was used, what the temperatures are, what the gas mixture was, all that detail.
And if more than one guy welds on it, yeah, could have easily more than one guy working on the same weld.
Oh yeah, for larger systems. So all that has to be tied to the specific weld. A spreadsheet has to be developed that indicates all that information. The weld procedures themselves are in there, and then whatever NDE, and if you have equipment that needs to be certified, is in there. A couple more terms just to throw at you guys. You may run into these at some point. LDAR systems are typically a jacketed system where an owner is conveying a category M fluid that's highly hazardous or toxic to human health, and therefore they have to make visual inspections on a routine basis and or put other means to detect leaks or breaks in not only the piping system but every joint and every valve. A lot of insurance companies require these for certain fluids. So it's yet another layer of documentation that needs to be put in place for some systems. You run into it every once in a while. I used to work in a phosgene gas plant. We had LDAR in that plant, and where we made Ultem plastic, we had a chemical called OCB, and if you touched it, you basically died. It was very, very bad stuff. So you had to have full PPE on. If it got on your bare skin and got into your bloodstream, you were dead. That's the kind of system gets held in. Car seal program. So you guys have heard of lotto procedures. So in some cases, an owner may want to keep a valve locked open or in a locked closed position during operation to mitigate risk. So I'm talking about these risk assessments. So in the pharmaceutical world and the industrial manufacturing world, on a system-by-system basis that's carrying category M fluids or any fluid really that touches the process, an owner has to sit down and develop a documented risk assessment of what can happen. What happens if the pressure is too high? What happens if the pressure is too low? What happens if we get a break? What happens if this valve is shut inadvertently and this one's open? And it will cause these different conditions to occur. And they do a complete fishbone analysis, and usually what shakes out of that is they'll find 2 or 3 valves that just absolutely have to be in specific positions, or something very bad could happen. And so they develop a car seal program to ensure that the operators are leaving those valves in the right positions. Okay, let's jump into 31.1. So this is also known as power piping code. You have to use this system when you're in a boiler plant, and usually it's off the boiler to the second valve per OSHA. So when you buy boiler trim, you're buying a OS and Y valve and usually a slide gate valve. That piping from that boiler to that second valve has to meet B31.1 requirements, and most manufacturers will provide those for you. Any steam distribution system, so you get past that second valve, anything above 140 psi requires compliance with this code. If you're working with steam in a nuclear facility, any steam in a nuclear facility is regulated by NRC. NRC requires B31.1. We don't do nuclear work here. And most municipal systems require it. I first got introduced to this code when I was working on Busch Stadium. And the Trigen loop is about 475 psi. So we had to tap into that loop and develop our steam stations. And every bit of that piping had to adhere to this particular code. When I worked in the power plant, chemical plant, this was 140 psi was our medium pressure steam system. We had 600 psi steam, which was high pressure, and then we had 185 psi loop, which was medium pressure for us. So anything on the medium or high pressure had to meet the B31.1. You find it a lot on college campuses just from a risk standpoint. They don't want their students getting hurt. This code is closely related to the boiler pressure vessel code. In almost all cases, the client is responsible for their own specs, what they want for NDE, above and beyond code minimum, the fluids that they want for testing. You get into these jobs and these clients have no idea what their options even are. So a lot of times we have to counsel them and give them some guidance on this is how you need to handle these types of systems. Covers us, covers them. You'll find a lot of the HJs don't know how to inspect this equipment. So this comes down to your state boiler inspectors and the insurance providers and the owners themselves that are self-governing based on OSHA compliance. Anytime you have a B31.1 system, you have to perform a pipe stress analysis, which is going to include all of your restraint and blocking. So if you've ever had the pleasure of starting up a 600 psi system, you'll see it move and you'll understand what blocking's for. It's interesting, the noises that come out of that system. But it has to be safe so that the joints don't fail when it grows and expands. According to B31.1, all hydronic testing is 1.5 times the system design pressure. There is no adjustment factor, if you will, B31.1. Your engineering turnover package must contain the following items. for any B311 system. Your weld continuity log pretty much says it all. You have to have your stress counts. Every weld has to be visually inspected by an AI, certified AI. And the AI also inspects the NDE films. It's usually radiographic with 311. So if you're doing an ultrasonic test or radiographic, somebody has to get that film and interpret it, and then that film has to be tagged and logged in with what weld it belongs to relative to the isometric drawing. There has to be a defined testing procedure in place that everybody signs off on, and of course, all of the testing is documented, fully documented and signed off on by all parties. So with B311, it's really a safety thing. You don't want somebody getting killed. Icon Mechanical accidentally hit the Trigen loop downtown St. Louis with a backhoe, and that 400-pound steam went up the side of a 3-story building, and it burnt the brick off the building. So you can imagine if there's a small crack on a steam system like this, you're dead. It's going to cut right through your body.
And it covered a building with asbestos. Remember that? The whole building.
Yeah, that was a mess. So if you get into any of these higher pressure steam systems, just be cognizant of the fact that there are a lot of extra special requirements. Okay, moving on to the next section, B313. So this is what a lot of people call the process piping section. This is where it applies. You're going to find this in your refineries, your chemical plants. Pharmaceutical is going to have B313 in it. Any manufacturing facility that deals with category N fluids is going to have B313 piping in it. So, and what you'll find in a lot of industry, like pharmaceutical, for example, you'll have a little bit of 31.3, a little 31.5, a little 31.9. They have a mixed bag. So you have to look at each individual system and treat it per its individual code section. A lot of these industries, like the chemical and refinery industry, they don't want to dink around with mixing and matching different code sections. 31.3 is very stringent, so they'll just follow 31.3 on every single piping system in the plant, whether or not it touches the process or not. It's just easier for them to just treat the whole plant as one type of system. So you're going to have your pipe stress analysis when you have systems that undergo thermal expansion. This is where you get into really needing the owner to define the NDE requirements. And I've been doing this for 25 years almost, and what you find is only about 30% of the owners actually know what their own requirements need to be. So both on the contracting side and on the consulting side, a lot of times I was counseling the owner as to what minimum requirements are. You get into a larger plant, like a BASF or a DuPont chemical, they're going to have the requirements nailed down. But some of these smaller satellite facilities, they really don't know what the code requirements are. And again, these codes are in place to protect us and to protect them. So if somebody gets hurt, we're fully documented. As I mentioned to a couple folks on this Arizona beverage job we're doing, some of these codes are also put in place to protect us financially. It's not just loss of human life or injuries, it is loss of product. So when I was doing pharmaceutical work, if we had a leak, it was multi-millions. Somebody had to pay for it. So if you weren't fully documented, you were at risk as a construction installer or an engineer. Again, it's closely related to the Section 8 Boiler Pressure Vessel Code. What you find is the hydrostatic testing is 1.5 times the MAWP, which is defined by the engineer designing the job times the R sub R factor for category influence. So if you have a hot water system or a category influence system that's operating at high pressures or temperatures, you have to adjust the testing because the stress that pipe or vessel is going to undergo at the higher temperature is different than what it is at ambient temperatures. So we have to define those as the engineer on the job. And as project managers, you guys need to be asking for this information so that it's in writing and you know exactly what you're supposed to be testing to that meets the code. So it's very important. Some owners require category D fluids to be tested as well. In pharmaceutical, there's usually a break between category D fluids that touch the process and don't touch the process. So we call it black utilities and clean utilities. So a clean utility might be category D, like compressed air, but it's still treated as a B31.3 system. So you have to kind of drill into it on a system by system basis and application by application basis with the owner and with the engineer to fully understand what your requirements are out in the field. 31.3 tells us that flange joints are not required to be tested if the job is spooled and assembled on site, which is nice. However, for your welds, for any category M fluid, you can't have any blind welds in the system. So a blind weld is basically a weld that you can't get a borescopic inspection to, which is a camera that you send down the pipe, or a weld that you cannot get a radiographic inspection of. So that's considered a blind weld. So as you're developing your sequencing of construction for big systems like this, and if there's a borescopic inspection required, for example, you have to make sure that it's built in such a way that the 25-foot borescopic camera or 50-foot camera can always get to the welds that you're laying. So how it's actually put together in a field becomes somewhat of an issue. You can't work over here and over here and over there and then join it up in the middle. You have to work from one side and work your way back. So it's just something to think about. So you have to be thinking about your NDE requirements before you even start construction. A lot of times leak testing will go on for 30 minutes, 2 hours. I had an owner wanted leak testing done overnight. The code only requires 10 minutes. So you can remind your owners of that. Here's the information that would be in your turnover package. Now, I say that it may contain these items, whereas on B31.1 it must contain those items per code. With 31.3, because the specs are client dependent, so are the contents of the ETOP package. Now, some people may look at that and say, well, for us, a hydrostatic test, signed off hydrostatic test form is a must. We're not even gonna let an owner tell us they don't need that, because if that pipe springs a leak under the warranty period and somebody gets hurt or have to shut down production, we're on the hook for that. What you'll find in 31.3 systems is the NDE is usually ultrasonic. And we touched on this on a different session, but the delivery execution strategy for manufacturing work, pharmaceutical work, is different than it is for commercial work, which is B31.9 for the most part. So fabrication ISOs may or may not be part of the equation. But clients may require it. So it's a good question to ask if you're bidding any of these types of systems. Where I worked at the chemical plant, we didn't have overhead drawings. We didn't do mechanical overhead drawings. We built the entire job off of fabrication ISOs. Can you imagine building? All we had was a GA that showed where the equipment was, and all the spools would show up. We'd get 2,000 or 3,000 spools, and a well continuity log, and the guys had to figure out how to stack up this piping and get it installed. There were no overhead drawings at all. So it depends on the industry, it depends on the delivery method.
And those include the PNIDs showing where all the devices were. Yeah.
PNIDs and fab ISOs is all we use. So it's a good question to ask if you're getting into some of this work. For BPE, so this is also part of 31.3. Anytime you have a clean utility system that follows current good manufacturing production practices, you're going to need to think about BPE. And here I kind of touched on the black utilities, clean utilities versus black utilities. There's a spec break there. There may be different testing requirements. So for certain types of work, like food and beverage, pharmaceutical, the FDA drives a lot of this. So owners have to comply with FDA requirements. The FDA is changing their position a little bit. They were becoming a prescriptive organization that laid out a set of specs, but what they found is they really couldn't apply specs to every single market sector, so now they're turning it around on the owners, and they're telling the owners, you need to develop a list of specs based on your risk analysis, and then they just approve the owner's documentation. So the FDA is stepping back and becoming more of a oversight branch of the government. And that's following very closely in step with how Europe has done it for years. So what are these requirements? So it's the categories of the fluids in some cases. It's the test pressures, operating temperatures and pressures, PSV set points, system design pressures and MAWPs, the NDE requirements. It's everything I've discussed that becomes part of your ETOP. All that needs to be from the owner. So if there's an engineer involved, 99% of that's going to be in the engineer spec. If there's not an engineer involved, and we're doing this kind of work, we need to develop this information hand in glove with the owner. For BPE work, I've changed the wording to it must contain. These are FDA requirements. There's a new one up there, passivation reports. So when you're dealing with stainless steel systems, like clean water systems, RO water, USP1, USP2, and WFI water systems, they require cleaning of the stainless steel piping on the inside, because during the course of construction, bacteria or bugs may have gotten in the system, so they use nitric acid or citric acid, and they circulate that system, they heat it up, and they kill all the bugs that are inside of that system. And those systems have to be periodically passivated as just a normal course of doing business. Any system that conveys product, if we get into stainless steel tubing that is conveying, like in the food and beverage industry, we're doing this Arizona tea. Had we gotten into the product conveyance of the sugars and the sucroses, those systems have to be passivated. Or if we would have gotten into the clean in place systems, there's a lot of distribution piping for the clean in place, CIP, those systems have to be passivated. Usually your NDE is going to be radiographic and borescopic. Because the welds are such a high purity weld, they use an orbital weld machine, and where the butt end of the joints come to one another, you actually have to lay a camera in there and see if there's any weld spatter that's popped up on the inside of that weld, or if there's any gap. So owners usually require 10% of the welds to be borescopically inspected, sometimes 5, sometimes 100. Obviously, that makes a big difference in cost. So, I wanted to touch on Section 8 Boiler Pressure Vessel Code. So Section 8, Division 1 and Division 2 applies to any boiler or pressurized vessel associated with any system. This is a very important code that is many times not self-regulated very well by all the owners that are out there. I'll just put it that way. You guys might remember in St. Louis 3 years ago, downtown St. Louis, a vessel exploded. It went 60 feet in the air. It traveled 3 blocks. It landed on another building and it killed 3 people. Okay, that vessel was not in compliance with Section 8, is what the finding was. They did a vessel inspection. A company was asked to put in a patch plate on that vessel. They filed the R1 for the use stamp to keep the vessel legal, but they advised the owner that they have several spots that are thinning out, and they, in writing, advised that that vessel be replaced at the earliest. And unfortunately, the owner did not want that expense. The boiler operator in charge of that boiler system also died during that event. So pressure vessels are kind of a big deal. The test pressure is calculated a little differently. It's MAWP times 1.3 times LSR. The code actually allows the design engineer to determine the MAWP for Section 8. So even though you have a system that's operating at 110.5 PSI, you're probably going to get a 125 PSI vessel. So you can always increase the MAWP if you need to. So anytime you're buying a U-code stamped vessel, which means it's a Section 8 vessel, but it's also gone through the additional testing to receive the ASME U stamp, which is stamped to the side of the vessel, it requires a documented pressure test, and so there will be traveler paperwork with the vessel itself. When the vessel ships, it's our responsibility to ensure that the nameplate is intact when we receive that vessel. Owners may require U-code vessels based on application or function. For the case of Arizona, the compressed air system is a 31.3 system, comes in product contact. All the vessels on Arizona are U-coded stamped vessels. So you're gonna, when you get into these industries like pharmaceutical or whatever it is, outside of commercial, typically they're going to want all their vessels to be U-stamped and protected because of liability.
Quick question.
Yep.
Back on the MAWP being determined by the design engineer, is that like the engineer designing the pressure vessel itself then, not the person ordering?
It's the person ordering it. It's the design professional responsible for the process.
Okay.
They can define it above the calculated minimum code value.
Okay.
A lot of times it comes on down to availability of the vessel, because you can buy a U-stamp vessel that's 125 PSI. It's already been tested. It's in stock. You're not going to find one that's a little off based on your calculation.
Yeah.
So.
Just wondering for the propane tank that we're getting in Newcastle.
Oh yeah.
I need to look at that paperwork.
So one thing to consider, you think of vessel, you think of a big contained vessel. It's not just the large tanks. It's any heat exchanger, any part of the system that is defined as a boiler or a reboiler, or is larger than, I think it's 4 cubic feet in volume, then it's considered a pressure vessel by code. So if you're less than 4 cubic feet, then you do not have to adhere to Section 8. It also does not apply to any atmospheric vessel. So even if you're under a slight pressure, like a condensate receiver, if it's been in the atmosphere, so it's never enforced on your commercial projects. But I wanted to point out that it's still a code requirement. So I've got another training I'll put together on how to design and select PSVs, pressure safety valves, for the vessels and the systems. It's a whole other training session. So for Section 8, your ETOP must contain the following. I don't know if anybody's had the pleasure of doing a deep dive on a set of vessel shop drawings, but they're very involved. You get into a lot of corrosion allowance calculations, and you have to get down to the details of how the welds are laid, what kind of weld it is, what weld procedure goes with that weld, if there's plates on the vessel that are welded on the vessel, how the end bells are taken care of. There's a lot of detail that goes into these. And of course, you have to have your certification. The PSVs themselves, which would be part of that separate training, they are their own separate device that gets attached to protect the vessel. So I'll talk about that later. All right, let's jump into 31.5. So this is for refrigeration piping. Refrigerant can be anything that can accomplish the heat transfer. We're seeing flammable liquids being used now, and slightly flammable liquids. Methane gas is a refrigerant. CO2 is a refrigerant. So if you have any kind of a distributed refrigeration system, it's going to fall under this code. It does not apply to packaged equipment that's been UL or ETL or CSL listed. So rooftop units are off the hook. But if you have any of these other refrigerants, you need to be thinking about it. And by the way, not only does it need to comply with 31.5, it also needs to comply with 31.3 from the ETOP standpoint, because they're class category influence. So kind of the same story as 31.3 for the hydrostatic test. Now with refrigeration systems, because they're much smaller, it is commonplace to pneumatically test them if it's a small system. And a lot of manufacturers also require a vacuum test prior to startup. So I'm thinking of like your VRF systems, variable refrigerant systems. I've never had the pleasure of doing a helium test, but it's another ASME 31.3 test method that can be used in conjunction with pneumatic testing. Pretty much the same story on ETOP. All right, so now we're going to talk about what we normally deal with. Category or B31.9 fluids. So this is going to be all your category D fluids. And again, they can exist within a pharmaceutical or manufacturing facility unless the engineer or the owner requires it meet 31.3, and we can follow 31.9. And of course, if it's required to be covered by 31.1 or 31.3, we're still on the hook for those. So I'm just making the point that 31.9 can be applied to even projects that have 31.5 on them. The test procedures are totally different. Now, for B31.9, the requirement is whatever the engineer wants to set it at. So it is typically 1.1, 1.25, or 1.5 times the operating pressure, not the system design pressure. So if you have a hot water system that's got a pump on it, and the pump is generating 75 psi deadhead, You might have a PSV on there that's set for 95 psi. Okay, it's a B31.9 fluid. It doesn't meet the temperature or the pressure to become a category M. So you're good with that. You may test to 1.5 times that operating pressure. So it's really up to the discretion of the engineer or us in the case of design build jobs. The fuel and gas code does still require 1.5 times the maximum working pressure because natural gas is a category M fluid. So you really have to check your codes. If you're fully compliant with the codes, then you're going to be hydrostatically testing your natural gas systems. But nobody ever does in commercial work.
Right.
You never see it done.
No. Can't get the water out.
Right. So typically with B31.9 systems, the pressure vessels are only protected to meet the minimum pressure vessel code requirement. So if you buy a boiler from Midwest, it's going to be a Section 8. It's going to have its own pop valve on it. No special calculations, no special anything. It just meets the minimum requirements because of the 31.9 system. I mentioned this before, but if you're on what's called an OSHA PSM site, which is any manufacturing site that contains large quantities of hazardous material as defined by the building code. So in the early chapters of the building code, there's a huge chart that has all these different chemicals, and it tells you how much volume you can store on site and how much you can transport around your site. And if you are over those values, and you have enough of those chemicals on site, then you have to be following the the PSM stands for Process Safety Management. And you have to be in full OSHA compliance. Now, if you're doing a small, say you're doing a small manufacturing facility where there's one hazardous room, and they got drums in that room. The room itself is considered to comply with the building code, so it has to have blowout walls, it has to have special exhaust and all that. But they may or may not have enough of that one chemical to classify them under the OSHA. So usually OSHA PSM sites are your large manufacturing facilities, refineries. We don't get into a lot of that work here. But it's good to be aware of it in case we're getting involved with a large project, just to clarify, because PSM has that much higher stringent level of compliance with all the installed systems. You may end up with some pressure test certs on your B31.9 systems. Sometimes they make it in, sometimes they don't. It's not a code requirement for B31.9. So that's all I've got. So I left a half hour for discussion and questions. I'm going to go to the beginning of this presentation. Did anybody have any questions about any part of what I talked about today?
Eric, where would our Rockwell boilers fall?
So the Rockwell boilers come in direct contact with the process. There's a process heat exchanger on Rockwell.
And that's considered direct contact?
Yes, so I had to go back to the owner and ask all the questions. But the owner did something very smart. They have their primary process, which is circulating the hot oil. Then they have a secondary process, which is a brine solution, that's circulating the heat to the roof-mounted condensers and to our heat exchanger. And then we're on the B side of that heat exchanger. The heat exchanger itself, according to Rockwell, and I have this in writing, does not require a PSV to protect the B side of that heat exchanger. Because when they did their risk assessment, they found that a single process failure did not exceed the pressure and temperature that the vessel could withstand. And there is no fire case to consider. In other words, they're not worried about a fire starting next to the heat exchanger and heating up the fluid that's inside the heat exchanger to a boiling point.
So even if somebody closes the valves, there's no danger there, and to not have a pressure relief valve?
I have it in writing from the owner. I happen to disagree with the owner in this case, but I have it in writing from the owner.
Even if something doesn't heat up the fluids, if the fluids increase in pressure, it's stuff that'll still boil.
That's correct.
Must be one tough heat exchanger. It's a
So-
shell and tube, right?
It is a plate and frame.
Oh, it's a plate and frame? Are you shitting?
So,
My
you know,
God.
my initial assumption was that our hot oil or our building heating system was a B31 3 system because the process temperature is over 400 degrees Fahrenheit. So if there's a failure of a valve, my thought was, oh, the temperature in that heat exchanger is going to quickly come to boiling. And for a sustained period of time, I could circulate that around the building and create risk all over the building. So initially I went at the owner with, this was not in the documents, but we need PSVs on all of our storage tanks, which need to be Section 8, in addition to our boiler, our expansion tanks, buffer tank, and the piping system needs protected for this condition, and a PSV on the B side of that heat exchanger. So I had a bunch of back and forth with the owner, and the owner said, nope, you're B31.9, you're fine. And I said, well, send that to me in writing.
Yeah, I guess the gaskets on the plates would fail first. I would think you just have oil and shit spraying all over the place.
Yep. So we have a PSV on the boilers in case we have a boiler failure, and then I have in writing that the pressure and temperature will never get us into a boiling situation. So, but we had to know to ask the question,
Yeah.
because if we didn't have that in writing, the owner would say, oh, well, I'm just an owner, I didn't know any better. You're the expert,
Right.
you're the design professional, you should have told me. So if somebody gets hurt, we're
Right.
on the hook for it.
Right.
I mean, we live in such a litigious society these days. You really have to protect yourself. When I was at Rock Hill, they did all the steam plant work up in Emerson, and a guy was using a Johnny bar on a steam gate valve that was 25 years old, and he busted the bonnet, and he got burned. Rock Hill had to participate over $1 million in that lawsuit. And that system was not designed by Rock Hill. The engineer got sued, everybody got sued. So the more documentation you have, the better you are during the discovery period in your depositions with the attorneys. I've been in 3 depositions, they're not fun.
That's true. I've been in one. It was enough. But one thing to remember for you guys, you're getting into all this stuff and you're seeing that codes require you to go to a higher level of design or testing or anything. Make sure when you turn that over to estimating that you tell them that, because all this shit eats up man hours like fucking crazy, especially when you have to go out and hire a team or somebody to do non-destructive testing or St. Louis Tech, whoever it is. All that shit really impacts the cost of the, you know, the job. So
Yeah, we're doing
that's
a
the biggest thing that I would bring up. I mean, other than knowing the right thing to design, make sure that everybody down the line knows it, and it gets, the cost of all that gets into the estimate. Because the poor project manager at the end is the guy that's got to explain it.
Well, and another key point to that is this stuff costs money, but it also takes a lot of time.
Yeah, it's a man hour fucking shark. It just eats you up.
So if you're on a job with this type of stuff, or where you have documented testing, you have to build that extra time into your schedule so that you can execute all of this properly. Because the last thing you want is somebody getting hurt and we're not documented, or causing loss of product.
And it costs an overhead too, because you got to have somebody there documenting all this shit, getting it all out to the right people, and then it's a big fucking deal.
We have a large propane tank on Newcastle that we're getting. Definitely need to go through. I guess Section 8 is what that would be under.
NFPA has some stake in this. International Fire Code has some stake in this. International Building Code, ASME Code Suite. You're going to find that all of them kind of play in this arena a little bit. And like I started off the presentation, they use different terminology. They may even conflict with one another. So you have to, when you get into this manufacturing work, you have to drill down and define it, early so that you know exactly what your plan is.
And the more that's on the drawing, on the cover sheet, when the building plan reviewer reviews it, and the mechanical guy reviews it, everybody's okay with it, and then the fire marshal shows up. Now, throw all that shit out the window, we're gonna do it my way. But if you have it all on there, you can open it up and say, look, we followed the rules, now you're changing the rules.
Yeah, and then you get paid for the changes.
Yes,
Whereas
right.
the other way,
have
you
it
don't
on
get
there.
paid for the changes.
Right.
Usually has a bigger stick and a louder voice.
Fire marshal has the biggest voice.
Actually, already went through the process of getting it approved through the fire chief. So hopefully that'll help with any fire marshal issues.
And another thing you run into, Matt, and what we ran into on Rockwell, because I brought this up early, when I worked at the chemical plant and it happened on Rockwell, the drawings and specs need to go to the insurance provider for their review as well. So usually it goes to the state fire marshal and the insurance provider. And you'll get, 5 or 6 pages of comments back from the insurance provider. Now on the Rockwell job, Rockwell's taking the position that they are going to respectfully disagree with every single recommendation made by the insurance provider, AKA their rates are going to go up.
That's interesting.
A lot of owners will actually try to work with, Alliance or United XL or whatever the name of their insurance company is, FM Global, and that will allow them to keep their rates down low. But there's a negotiation that happens there, and that can cause delay in construction and execution of the drawings, because insurance guy may want to see, this particular system follow B31.3 instead of 31.9, even though it was bid with 31.9. That just may be a carte blanche, this is what we want to see. Well, usually the people that are reviewing that paperwork don't understand the ramification.
They just say,
So we've got to point these things out and assign the cost to it. So that's why on Rockwell, I wanted to be involved with the insurance review. Because anytime you're in a large industrial or manufacturing, there's going to be a review, and we need to have a seat at the table. All right, well, I recorded this, so I'm going to send out a recorded version of this, and thanks everybody for your time.
Thanks.
Thank you.
Thanks, Eric.
Sure.
Thanks, Eric.